Okay, Boris, so happy birthday once again. And I'm very honored to be present at this conference. Um, I will present some results that I am pursuing for last at least 3 years with my students. And this is a model-free approach to design. So, kind of situation that we are considering. Actually, I should tell you the background of how I came to open up this line of research. I was teaching circuit theory to undergraduates about six years ago for the first time after many years. So, in circuit theory, there is a classical result called Thevenin's theorem. And Thevenin's theorem is you can have a network of arbitrary complexity, but if you want to know what will happen if you connect an element between two terminals, all you need to know is the so-called Thevenin equivalent, which is you can replace this entire network with one source and one impedance in series with this. So, if you know these two parameters, you know the behavior of the network between these two terminals regardless of the complexity of the actual network. You see, it's a beautiful result, and after many years I was teaching this, but I couldn't find a proof of it, even in the wonderful book of Desor. At some point the proof appeals to you to accept something. And even superposition principle, there is some hand waving in the circuits literature. So, I set out to prove Thevenin's theorem myself. In the process, I discovered that it follows very simply from Kramer's rule, and which is a property you can do for linear systems, since many engineering systems are described by linear equations. You can have a Thevenin-like theorem for mechanical systems, hydraulic, thermal, economic, ecological, and so on and so on. But more importantly, Thevenin's theorem has a special structure. You connect between these two terminals, and the description of the network is between these two terminals. But the problem I started considering is, let's say you have an unknown system and you want to add a new element to this. You have a circuit already mostly built up, but you're going to add some resistive elements with the objective of controlling currents or voltages or power at some points in the network. Is it possible to answer this question without knowing this unknown system? And the answer is yes. You can take, because the mapping of these variables onto these design parameters is quite a simple mapping. It's a well parameterized mapping. If you know those parameters, you know the function, and then you can invert the function. So, this is the kind of result I am going to present. Just to illustrate, for example, you have a distribution network for water in a city, and you are contemplating adding another line. How do you size this pipe to ensure that certain amount of fluid will flow, or distributions in different places will be under control? You don't know this network. You have to design this extra element, right? You can answer questions like that very nicely. Okay, so let's go. I have many slides, so if I run through some of them, please excuse me. So this is joint work with my former students from 30 years ago, 40 years ago, and 2 years ago. Um, so some motivation. We can directly design these new elements without identifying the system. That's the new measurement-based approach. Some applications to AC, DC circuits, linear mechanical systems, robustness analysis, and fault-tolerant design, and to control systems also. So usually we start with a most of the fields, engineering fields, are based on having models. And so now, in order to do any design, you have to first have a model. But sometimes this is a self-created problem. If you formulate the problem as, I got to design something, I don't care about the model is fixed. What I'm going to add is what I need to find out. So if you take that point of view, you can many times bypass this modeling process. So let's proceed to say you have an unknown linear system. You're going to add a new element. You're interested in controlling this variable. This variable could be currents, voltages, power, displacements, flow rates, transfer functions, and the design elements could be circuit elements, mechanical elements, transfer functions, dynamic systems. We want to connect a new element to achieve some certain types of variables to be within some limits. So the whole thing is a question of finding out the functional dependence of these things without really identifying the system, because the system is fixed, and the effect of the fixed part of the system will manifest itself in this relationship. And by a few measurements, you can extract these parameters of this relationship without really explicitly knowing the system. So let's say you have a complex circuit. You are interested in the current in this branch. You are interested in the current in branch 9. Where is 9? Here. And your design variables are L1, C2. If you can find out these functional relationships, you can invert them, perhaps. So objectives are to analyze and design problems in linear systems without requiring a mathematical model. A few preliminaries. Let's say A is a matrix with a parameter P, scalar parameter, which enters the matrix A through this matrix A1. If you take the determinant of A, it's going to be a polynomial of degree at most r in P. It's easy to show, and you can extend this to multiple parameters, and you get a multi-polynomial form like this, where the R1s, which are the degrees of these parameters Pi, R1, R2, etc., are the degrees of P1, P2, depends on the ranks of the matrices A1 through AL, the way it enters. So let's say you have a linear equation like this in n variables, n equations in n variables. The Q's are sources, and typically they occur in this form in the right hand side, and the P's are as before, X's are the system variables, and we assume that AP is non-singular over the range of variations of P that are of interest. Otherwise, there is not a unique solution, and you are not talking of a physical system. So a point here, this form of B is typical, and in fact this is the basis of the superposition principle in circuit theory, that Q's appear like this. There is no constant term B0. If B0 is there, it's no longer obeys the superposition principle. So this will lead to a precise definition of what is superposition principle. So you solve for x of I, and it's a ratio of determinants from Cramer's rule. And if you can evaluate these determinants, they are polynomials in P and Q. If you know the coefficients of the polynomials, you know this solution, and the coefficients can be determined by taking measurements. So basically that's what the talk is all about. So the solution for xi is the ratio of polynomials. It will be linear in Q, because when you take the determinant, the Qi's appear linearly, and it will be polynomial in P. So if you have mu unknown coefficients in those polynomials, you can attach elements to the system and take measurements, and then form an equation to extract the coefficients. Okay. So in that sense, it is a measurement based approach that directly designs the design elements. So we have a monograph that appeared last year, a Springer monograph describing this line of research. You can do this in a what looks like a state space form, except this is static. So this is also described. You can consider interval parameters, design parameters, and interval inputs, and you get a functional dependency like this, which is relating the output vector to the input vector. So for example, focusing on y1, it's of this type. The coefficients betas and alphas are the ones to be determined, and they can be determined by setting, for example, the second input to 0, first input to be some particular input, and then set 7 different sets of parameters and measure the corresponding outputs. Then you can form a measurement equation, and solving that measurement equation, you can find the parameters alphas and betas. Okay. So this measurement equation has to be well conditioned, it has to be invertible, of course, and so on. So there is some research to be done on what are the good measurements, because if this matrix is ill conditioned, you don't get reliable coefficients. So here we are, DC circuit, unknown system. I want to control the current here by adjusting this resistor. It turns out that in these circuits, these branch resistors appear in the matrix A always with rank 1. Why? Because I can write down the branch currents, IJs, branch voltages, VJs, etc. The resistor Ri will appear only associated with current Ri, right? And so it will appear only in column I. It will always be rank 1. And regardless of the complexity of the circuit, you can have million branches, but each Ri will appear with rank 1. I'm saying this because we submitted this paper to a circuits journal, and the reviewer says, well, since you are considering only rank 1, you can only do simple circuits. That's not at all the point. It is generically rank 1. Only in very odd cases you might get rank 2 or 3, and it's not a problem to handle that. But you know, reviewers are nowadays so anxious to reject your paper that they immediately, but it's a foolish statement to make. Um, so because of rank 1, this is going to be a ratio of polynomial of degree 1 over polynomial of degree 1. So 4 coefficients normalized by dividing with 1. You have 3 coefficients. 3 measurements will extract those coefficients, right? So that's what we are saying here. So the form of the solution is like this because of the rank 1. Rank 1 is a generic property. In fact, in almost any network, even a hydraulic network, this is true. The resistance Rj will occur with branch Ij. So by problem formulation, it is rank 1. Anyway, it doesn't make sense if both these betas are 0. So you can divide by 1 and reduce to 3 parameters. And then you take 3 measurements. Set R to 3 different values, measure the currents, and form these equations to extract the alphas. And then you know the relationship. Okay? There are particular cases of this when the measurement matrix is singular, etc., etc. But generically, it is 3 measurements. In Thevenin's problem, the resistor Rj occurs at the terminals. The control resistor occurs at the same place where you make the measurement. And in that case, one of the numerator coefficients is 0. And so it takes this form, normalized to 2 parameters. And that's why Thevenin's equivalents have 2 parameters, voltage and current. When you learn undergraduate circuits, they always say, measure the open circuit voltage and the short circuit current. You know, in most circuits, you cannot do that. But this analysis shows you that any 2 arbitrary measurements will do. You don't have to open circuit and you don't have to short circuit. So the interesting thing here is that when you have a relationship like that first order, this one, it has certain monotonic properties. If you take the derivative of the variable with respect to the design, it is sign invariant. Okay? And so this variable is always monotonic, either increasing or decreasing. And therefore, the maximum and minimum values will occur at the endpoints. Right? So this is, I can optimize this system, I can find max and min values without knowing the model. People who optimize, they always say, give me f of x and I'll find you the minimum. Well, I don't know f of x, but I can take a couple of measurements and I can give you the max and min. So this was kind of surprising to us, and circuits people don't really know this fact, that the currents and voltages are monotonic. I mean, if you ask a circuits guy, he'll not know this fact in general. Stephen is smiling because
some would.
Well, maybe Desor would. He is Desor's student, but not the average run-of-the-mill circuit theorist, right? Anyway, in Thevenin's problem, this is the situation. Rj and Ri are in correspondence, and so 2 arbitrary measurements suffice. Not necessary to do open circuit and short circuit tests, which are most often not feasible. What if you have 2 design resistors and you are trying to control current II? Well, you know that multilinear form, it's again rank 1 with respect to each resistor. So you're going to get multilinear in Ri Rj over multilinear in Ri Rj. You have 4 coefficients over 4 coefficients. Normalized with 1, you got 7. So 7 measurements of the 2 resistances and the current that you get will determine the system of equations, will determine the unknown coefficients. So that's how you get the measurement equation. And then depending on the rank of the measurement equation, if you have over parameterized and there are some special cases, you can handle those. Some of those coefficients could be 0. You will detect that from the rank of the measurement equation, because that corresponding coefficient, when you take the determinant, it's going to be 0. So the measurements reveal a lot about the system without revealing everything about the system. It just gives you the information you need to design your parameters and not more. So in general, for M design variables, you can take that many measurements, and you can extend these kind of results, because you have this this looks worse than it actually is. It is actually multilinear in all those parameters. This example was included because people said, well, there are situations where you have rank 2 dependence, for example, and there are circuit elements called gyrators. I was not aware of what a gyrator is, but the reviewer pointed out, why didn't you consider gyrators? So we looked up gyrators, and a gyrator is like a mutual inductance element. The voltage at terminal 2 depends on the current in terminal 1 and vice versa. So in that case, you get rank 2 dependency, and then you got to in the simplest case, you're going to have 5 measurements rather than 3, because it's going to be a polynomial of degree 2 over a polynomial of degree 2. Okay. What about if you're controlling, your control variables are sources? It's very simple in that case. This is where the superposition comes in. You just have a linear function of m parameters, and you can just set them to different values and find, with m measurements, you can find the alphas, alpha to alpha m. If you want to control power is I square Ri. So if you know the max and min of I, you know the max and min of I square also. And so since it was monotonic, the power will also be monotonic. Now in Thevenin's case, there is a subtlety, because it's I squared, but then it's multiplied by Ri itself, and because of that, you don't have monotonicity, you have a maximum. Again, the maximum can be found from those 2 arbitrary measurements by finding alpha 0 and beta 0. So you can have a generalization of this maximum power theorem. You want to maximize the power in this resistor by adjusting Rj. You can get explicit expressions for what to set Rj in terms, and it's all in terms of the measured variables. So, are you going to tell me when the time is almost?
About 2 minutes.
About 2 minutes.
No, actually 5 minutes.
Wow. So I am at 37, I have 104 in 2 minutes. Anyway, so let's run through these slides. Here I want to use R1 and R6 as design variables, and I want to control the power in these 3 branches, 3, 6, and 11. Okay, and I don't know this circuit, of course. Take some measurements. and find those coefficients. Then you have the functional dependency, and you can plot each power in this plane as a function of R1, R6, R3, R6. It shows the monotonic behavior in each direction, right? And then you can impose the power level constraints 40 to 60 and extract the design variables. You can do the same for the next constraint and the third constraint, and then you can intersect those to find the feasible range of design parameters. So this is really neat because actually nowadays there is a lot of preoccupation with designing low power circuits and etc. You can do these for these large scale circuits without knowing the model, with just measurement based. Okay, so another DC circuit. Let me skip these DC circuits. There's too much DC circuits. So again, this monotonic behavior tells you that the extreme points are at the extreme values of the intervals. The same thing for AC circuits, okay, except things are now, because Kramer's rule applies with complex numbers, and you have impedances and complex currents and voltages if it's a circuit operating at a fixed frequency. And so you can solve problems of this type. You can constrain the magnitude and the phase, and find out the range of design parameters for an unknown circuit. This is the functional dependency after taking some measurements with L1 and C2. And then you can do the same. This is magnitude versus L1, C2, phase versus L1, C2. You can intersect them, and then you can find the range of design parameters. You can do mechanical systems with, and then you can develop a Thevenin's theorem for mechanical systems. Mass spring systems. Again, you have a more complicated looking matrix, but basically it is rank 1. If you look here, it is rank 1 in K2, it is rank 1 in K3, right? And so again, you are going to get this type of dependency. So 3 measurements can solve that problem if you want to restrict the displacement and want to adjust the spring kg as the design parameter. This is like a civil engineering building. You want to restrict the displacement. It's equivalent to a mass spring problem. In truss structures where you want to control the displacement, you want to size the truss element, it is again a linear equation. So once you get away from circuits to linear equations, the whole world opens up to you. And all these problems fall under the same umbrella. The matrices look complicated, but we don't care, because we don't know these matrices. All we are interested is in the rank dependency. As long as that is a low rank dependency, you can extract the parameters from measurements. He's got up. That means I got to sit down. Okay, so 1 minute. So let us quickly run through truss structures. You can do hydraulic. You know, I told you about the adding an extra line to a hydraulic network. You can solve problem like that, controlling the flow rates. An interesting application is, so this is the hydraulic system design. You can design the radii of the pipes to be added. Robust stability analysis, the maximum minimum occurs at the corners of these boxes. Kharitonov would have liked that. Okay, fault tolerant design. If you have two, let's say you have a faulty element and you want to design an element to keep this variable between prescribed levels, whether the faulty element is on or off at a 0 or infinity, right, like short circuit or open circuit. You can solve a problem like that from the functional dependence. All right, all right. Okay, so
Just have 80 or 100.
let's go. So you can do control systems. An arbitrarily complex control system can be replaced by one like this. Okay. This means that stability is only related to beta. C must stabilize beta, and beta can be found from measurements from here. Okay, I'm going to run through conclusions. Thank you. Okay.